Hi and welcome to this run through of question 18 from our 2020 Synthesis and Analytical Techniques paper mock. So, before you start, it might be worth having a copy of the data sheet. This can be downloaded from the link that I'm going to put up now. Alternatively, you can just put it into a search engine and it'll take you to the same place. Okay, so at this point I'm assuming you have that in front of you, either on a screen or a piece of paper. So it's the NMR part of it you'll need a little bit later on. But I'm just sort of getting you prepared so that you don't have to suddenly pause and just check your data sheet. Let's just have it ready before we start. So the first part of the question asks you for the systematic name of ester A. So obviously the ester functional group is the one that I've highlighted in the middle. So the part to the right of the functional group there, which has the carbon single bond oxygen, is responsible for the first part of the name, which ends in YL. So there's two carbons in the skeletal formula of this part of the molecule, so that must mean it's an ethyl part of the name. So this next part is responsible for the second part of the name, which ends in O8. And there's three carbons in the skeletal formula of this part, including the carbon double bond oxygen, plus there's a bromine atom on carbon number 3, counting from right to left from C double bond O. So it's 3-bromopropanoate. So the next part requires us to have a think about some organic synthesis pathways. So I'm just going to move the page down a bit. And it says, draw the organic products for the reactions of the functional groups of ester A. So what you've got to think about is what happens when you add an acid to an ester, and what happens when you add an alkali to an ester. So checking our recall, we're obviously looking at acid hydrolysis and alkaline hydrolysis. So thinking about what this actually makes, you get an alcohol in the carboxylic acid for the acid hydrolysis. We can put those in now. And we can do the same for the alkaline hydrolysis if we just move the page down a little bit. So doing the carboxylate salt first. You've probably noticed something here while I'm writing this. So what's happened to the bromine? Well, if you think about what happens, that the OH minus behaves as a nucleophile, so the bromine gets substituted for an OH. Okay, so let's go on to the next part of the question. So moving it down, it says, name the type of reactions of ester A shown in part 2. We've already worked out this hydrolysis, so we can obviously add that in. So for this part, which is the part where quite a few people struggled, I'm assuming that you've got your OCR data sheet in front of you. So I gave you the link earlier. If you need to pause the clip and copy the link and paste it into your phone or your computer and download it and print it off or whatever, then that's fine. So from the data sheet, I've just put next to each of the environments what the actual, next to each of the proton environments, what the actual chemical environment is from the various environments that are printed on the data sheet. And each one will carry a certain ppm, a certain chemical shift value, and that's what they want you to put in there. So obviously the values don't have to be exact, they can be a little bit out one way or another. I think it's normally around 0.2 ppms either way that they allow. So now we've got to do the splitting pattern. So I'm going to do a little annotation underneath each of the environments using the n+1 rule. So what you've got to do each time is look at how many hydrogens are in the adjacent hydrogen environment that's non-equivalent. So even though, for example, there's two CH2s next to each other, one of the CH2s has a bromine attached to the carbon, the other CH2 has the C double bond O attached to the carbon. So technically they're actually different environments, so they're non-equivalent. Okay, so we need to move the page down a little bit and analyse this next part. So if I move it down, and then it says compound B is a structural isomer of ester A. So what we'll need to do is go back and get a picture of ester A and just pop it in here so you can see it. So remembering that compound B is a structural isomer of ester A, we now need to stop there and decide what the molecular formula of our compound is going to be. So that means we can use that as a reference point to check what we're coming up with. Now let's look at sodium carbonate. That means it must have a carboxylic acid group. And there's 4 carbon environments. Sorry, put it next to where the information is. And it says possible structure. So that might mean that there's more than one. So let's now just give it a go. Let's try it out. Let's start with COOH. So the trick to getting this question is to look at how many carbon environments you've got. But you've got 5 carbons. So 2 must be in the same environment. Otherwise you'll be going off all over the place trying to arrive at something. So that's one possibility. You've got 4 carbon environments. I'll just highlight them for you. So taking that idea, you can put 2 carbon environments in several different places. So looking at these possibilities, they can all fit the bill. So the next part, polyester, is formed from 200 molecules of 4-hydroxybenzoic acid. So this is moving on from that particular compound that we looked at just now. So 4-hydroxybenzoic acid, let's get a picture of that down. So 200 molecules of that compound would be equal to 27,600 grams. So what we've got to think about is what happens when it polymerizes. So when it polymerizes, one H2O eliminated per molecule apart from the end. So in other words, when you get a polymerization of 2 molecules together, you get an H2O eliminated. So that means that there must be 199 waters eliminated if 200 molecules of 4-hydroxybenzoic acid are going to polymerize in a chain. So that means that you've got to multiply the MR of water times 199 and then subtract that from your original 27,600. So if we put that in, that gives us 24,018 grams per mole. So this next part is a levelled response question. So you want ester C made from 2-methylpropanol. So if you remember, esters start from an alcohol and a carboxylic acid. So I've started off by looking at how you might create or synthesize the ester. Now you've got to work out how you're going to make 12.75 grams of that ester starting from the methylpropanol. So there's 2 parts to this. There's the synthesis and then there's the percentage yield. So step 1 is to oxidize the aldehyde, so the equation with the reagents and conditions as they've asked you for are included. So we need to now think about part 2. So I've put in the reflux with concentrated H2SO4 for the second stage, but if I'm going to say concentrated H2SO4 for the second stage, I've just gone back and changed my conditions for the first stage. It should be dilute H2SO4. So it's important perhaps to think about this. So the ester, there's 0.125 moles required. So I need to work out from the percentage yield what number of moles of methanol, 2-methylpropanol that I'd need to make that. So if there's a 40% yield, then 0.125 moles, normally, assuming 100% yield, the equation would suggest that 1 mole of ester is produced from 1 mole of aldehyde. But if there's a 40% yield, then you need to factor that in by multiplying the number of moles of aldehyde you'd normally expect times 100 over 40, so that gives you 0.3125. So that means that you'd need 22.5 grams of aldehyde. So let's do a quick check now. Have we done everything that we've been asked? We've got the mass of 2-methylpropanol required, we've got the reagents, we've got the conditions, and we've got the equations. So it's always worth double checking back with the instructions when you do these to make sure everything that's been asked for has been included. So now let's go to the final part of the question. So here they're asking you to look at the mass spectrum of ester C and think about what the possible structures for the species responsible for peaks Y and Z are. So you need to think about what the MZ value and the mass of the actual fragments are. So the mass of fragment Z is 71. So if we think carefully about the masses of each of the fragments and where from the molecule they could have come, that now allows us to write in what the fragments are. And that takes us to the end of the question, so hopefully you found it of some use to help you maybe untangle some of the parts of this question for yourself. But there's definitely some difficult parts in there, I'll give you that for sure. Okay, so as always, thanks for listening, and until next time, see you soon.